Welcome back to Integral Calculus. In this video, I want to talk about a couple of properties of series. First, a couple of specific series that I want you to be familiar with, and then a couple of general rules that are going to serve us moving forward. All right, so first of all, I want you to be familiar with a geometric series. A geometric series is any series that can be written in the form the sum k goes from 1 to infinity of a times r to the k minus 1 power. Sometimes you'll see this written as the sum k goes from 0 to infinity of a times r to the k. There's no better or worse way of going about it. They are mathematically equivalent. It's a change of variables. It's basically I did a u substitution, and they work either way. The reason that a geometric series is useful, it turns out that if in absolute value r is bigger than or equal to 1, the series diverges. But if in absolute value r is less than 1, not only do we know that the series converges, but we know specifically that it is going to converge to the fraction a over 1 minus r. So if I have something like the sum, k goes from, let's make it go from 0 to infinity of 3 over 5 to the k. It doesn't immediately look like the form that we had before, but if you play around with the expression a little bit, I hope you can agree with me that this is the same thing as 3 times 1/5 to the k power. And as soon as you can establish that, you know that a is 3, r is 1/5, and the absolute value of r is less than 1. Knowing the values of a and r, checking to see whether r is less than 1 or not, we can plug into the formula. The result we're going to get here is 3 over 1 minus 1/5. Doing a little bit of arithmetic to clean that up, this is 3 over 4/5, which is the same thing as 3 times 5/3. 3 times 5/4, which is 15 over 4. We are able to evaluate the series without having to do anything else, if we can recognize that what we have is a geometric series. Another one that I want to look at here, how about the sum k goes from 3 to infinity of 4 over 9 to the k minus 1 power. In this case, we have the k minus 1 power. I'll do the same sort of thing to rearrange it at the first place. But notice that this time we are missing a little bit. I've got a k minus 1 power here, and in the formula, when I have a k minus 1 power, I want k equals 1 down here. I don't have that. I have k equals 3. So here's where I'm going to play mathematicians' favorite trick. If I change that from a 3 to a 1, well, I can do that by adding a1 and adding a2 to the summation. I can't just add arbitrarily, but I can both add and subtract. So if I take the sum, I add a1, I add a2, then I subtract a1 and I subtract a2, it will take me right back to where I started. But by doing it this way, I can combine a1, a2, and the rest of the summation. And that's just going to be the sum, k goes from 1 to infinity, of 4 times 1/9 to the k minus 1. Right? The sum is already a3 plus a4 plus a5 and so on all the way to infinity. And if I add a1 and a2 to it, I can use the commutative and associative properties of addition, put them at the beginning and say a1 plus a2 plus a3 plus a4 plus a5 and so on to infinity. All right, so I have that summation, but then I still have to subtract. When I plug in k equals 1, I get 4, let's put it this way, 4 times 1/9 to the 0, and I get 4 times 1/9 to the first when I plug in k equals 2. Right? So the series itself is going to be evaluated using the summation formula. It's going to be 4 over 1 minus 1/9, and then I'm going to have to subtract 4, and I'm going to have to subtract 4/9. This is going to give me a really ugly fraction, but it is still a fraction, it still works. Also, why did somebody with my bad handwriting have to write 4s and 9s in the same expression so much? That is a 4, not a 9, and not a 7. All right, 4 over 8/9 is the same thing as 9 over 2. And let's see. 4 is the same thing as 8 over 2. So I have 1/2 minus 4/9. That's the same thing as 9 over 18 minus 8 over 18. And all told, that gives me 1 over 18. If you have a calculator that can handle working with fractions, having it do the arithmetic for you is certainly beneficial. I don't have mine at hand, so I had to go through it long ways. That's okay. It's just fractions. We can handle it. Up next, I want to talk about a telescoping series. A telescoping series is any series that we can write in the form the sum k goes from 1 to infinity of bk minus bk plus 1. And that seems like a bit of an odd thing to have, but the value of it is incredible. Because if we start listing this out, right, we're going to have b1 minus b2 plus b2 minus b3 plus b3 minus b4, and so on. And I'm going to take the partial sum here. So this is just going to be my Sn term, which is going to end at Bn minus Bn plus 1. But we've got a minus b2 plus b2 that cancel each other out. We've got a minus b3 plus b3 that cancel each other out. We've got a minus b4 plus b4 that cancel each other out. We've got a minus bn plus bn that cancel each other out. And the value here is if we have a closed form expression for b, right, for the b sequence, we now have a closed form expression for the sequence of partial sums, and we are able to go from there, which is incredibly valuable. So for example, if I'm looking at the sum, let's say k goes from 1 to infinity of the cosine of 1 over k plus the cosine, let's make that pi over k, that looks more cosine-y, pi over k plus 1. Well, this is a telescoping series, or it should be if I wrote it down correctly. I wrote a plus sign. There absolutely has to be a minus sign there. So I know that Sn, if I choose an arbitrary point here, I'm going to have cosine of pi minus cosine of pi over n plus 1. And even though cosine itself is an oscillating function and it doesn't seem like it gets much of anywhere, in this particular case it's going to work out fine. Because when I want to take the limit on cosine, I can bring the limit inside, and if I have something that works nicely, in this case I do, right? 1 over n, pi over n plus 1 still, is going to go towards 1 over infinity, which is basically 0. I'm sorry, yeah. So basically, I have cosine of pi minus cosine of 0 in the limiting sense. Cosine of pi is negative 1, cosine of 0 is 1, and negative 1 minus 1 is negative 2. So by identifying that this is a telescoping series, I am able to evaluate it without having to do anything else. Up next is one of the wrinkles that textbooks love to throw into series. It's called an alternating series. And an alternating series is a sum, k goes from 1 to infinity, of negative 1 to the k times ak. Where the ak themselves are either all positive or all negative. I'm just going to list out the terms of a quick example here to make sure that you understand what's going on. All right, so if I have negative 1 to the k over k squared, when I plug in k equals 1, I'm going to get negative 1 over 1, which is just negative 1. When I plug in k equals 2, I'm going to get negative 1 squared, which is positive 1, over 2 squared, which is 4. And then when I plug in k equals 3, I'm going to get negative 1 over 3 squared, which is 9, plus 1 over 16 minus 1 over 25, and so on and so on. We call it an alternating series because the signs, SIGN signs, of my terms alternate between positive and negative. I could have set it up slightly differently so that the first term was positive and the second term was negative. It's still an alternating series. And when you have an alternating series, there is a test called absolute convergence. It says that if the sum, k goes from 1 to infinity of ak, converges, then the sum, k goes from 1 to infinity of negative 1 to the k times ak, also converges. This is a bit of a disappointment result because it doesn't tell us how to get from one to the other. Right? The limit on ak and the limit on the alternating series, negative 1 to the k ak, might be different limits, and in fact almost certainly are different limits, and almost certainly there's no relationship between them. But it does give us a starting point, right? If we recognize that we have an alternating series that's based on a familiar series, right? A geometric series or something like that, that gives us a place to start. Another thing that you can often do with an alternating series is when you start listing them out, you might recognize that if you group pairs of them together, you might be able to rephrase the series as a telescoping series. It doesn't always work, but it's something to try. Finally, something that I'm somewhat ashamed to admit, when I was a student, I could not understand why did we call this absolute convergence. Well, what did I do going between these two? In my alternating series, I dropped the negative sign so that either everything stayed positive or everything stayed negative. So if I drop the negative 1 to the k, then this becomes positive and this becomes positive and the one behind my head becomes positive, and essentially I take the absolute value of every term in the series. That's all it means. If it converges when you take an absolute value before summing them, then it will still converge without the absolute value. That is too much to say, so mathematicians call it absolute convergence. The last thing here, I want to talk about linear combinations. Let's consider two sequences, AK and BK, and I want to choose these such that the series built on them each converge. So the series on AK, the sum of AKs, converges to L, and the sum of all the BKs converges to M. And let's also pick a couple of other values. Let's let P and Q be constants. Remember that a linear combination is some constant times the first thing we care about plus some other constant times the second thing we care about. So if I take a linear combination of my two sequences, that might be something like p times ak plus q times bk. And if I try to sum that sequence, the linear combination sequence, it turns out that as long as my original sequences formed series that converge, I can split the summation up let each of those individual components converge and get a convergent result. Right? P, L, Q, and M are all real numbers. They're all constants. So I have a constant value. This linear combination sequence must itself converge. So with all of those ideas in mind, I would like you to think about this infinite series. I've got the sum k goes from 0 to infinity of 3 over 5 to the k plus 4 over 9 to the k. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.